Hi everyone, today we are looking at parallel circuits, and you can see we start off with a simple circuit with only one resistor, and I want to connect another resistor in parallel. What does that mean? So a parallel, think about it this way, parallel circuit is when there is more than one path through which current can flow. You must give the current options in that sense. There are more than one path through which it can flow. And so if I want to connect another resistor, I must actually create space over here, and I'm going to move R1 up. Where should the second resistor be? The current flows. I must give it some option, so it can go through R1 or it can go through R2. You're giving it more than one path. So let's just label the current same way as we did in the series circuits video. When the current flows out, let's call this total current, or IT, T for total. And IT is the same here because there's nowhere else the current can flow. But when the current reaches here, it can split. So let's say the some current goes up. Let's call this current I1 because it's the current going through R1. And some current goes down, and let's call this I2, right? So I total splits to give I1 and I2. Some current goes to R1, some current goes through R2. And then when they reach here, they have to recombine back to give me I total. And I total goes back to the battery. Right. And so the key thing to note is this is I1 and this is I2. It's current splits. If it's hard to visualize, think about it this way. Let's say you have 10 cars driving out. 10 cars. 10 cars are still driving here, right? They have nowhere to go. They cannot drive off the road, okay? So they stick on the road, 10 cars. But when the 10 cars reach here, they can choose in some sense. And so let's say 6 cars drive up and 4 cars drive down. And then 6 cars reach here, 4 cars reach here, and they recombine back to give me 10 cars, and then the 10 cars drive back. So clearly, you can see that the relationship between I1 and I2 is that if you add them up, it will give you I total. This is for current. So once again, let's look at the question quickly, just to test our understanding. And let's say we have a simple parallel circuit. R1, R2. And I told you that the total current is, let's say, 6 amperes. And now I tell you that the current going through R2 is, let's say, 5 amperes. What is the current going through I1? You can pause and think about it. Okay, first thing to note is that this is a parallel circuit. And once you know that this is a parallel circuit, then you should see that I1 plus I2 equals to I total. And so I1 is simply, I don't know what it is, and I2 is 5 amperes, and I total is 6. So I1 must be 1 ampere. I1 equals to 1 ampere. There you go. Okay, so now let's move on to the next part. We look at current. Let's go on to potential difference. So let's go back to that same circuit, R1 and R2. Okay, and let's give values this time as we did before. And let's call this a 9 volt battery. Then we can label 9 here and 0 here. And so since this is 9 and it goes through a wire that has no resistance, so it's still going to be 9. It's still going to be 9. When it splits, there is no change, right? Because there is no resistance. Just think about whether there is resistance. No resistance, then it's still 9. It's still 9. Similarly, over here, it's still 0, 0, 0, 0, 0, 0, 0. What do you see? The potential difference, V1, which is across R1, and the potential difference, V2 across R2 is both 9. They're both 9, right? This gives me 9 minus 0 equals to 9 and volts, and this also gives me 9 minus 0 equals to 9 volts. And so what we can conclude is that this is the EMF, this is the battery's potential difference. We can conclude that the battery's potential difference is equal to V1, which is also equal to V2, yeah, for two resistors in parallel. So let me just write that down. This is for potential difference. So let's just jump in and do a quick question once again to just check our understanding. So we construct this circuit once again, R1, R2. And now if I told you simply this potential difference is 5 volts. This is my VE. And then question, what is V1? What is V2? Pause and think about it. All right, now you can see if first thing, recognize that R1 and R2 are in parallel, and then you can see that the potential here is 50, so all the way through it has to be 50, 50. So immediately you see that V1 equals to 5 volts, V2 also equals to 5 volts, because for two resistors in parallel, VE, which is 5 volts, equals to V1, which is also equal to V2. All right, so now let's look at the last part for resistance. Let me just construct that circuit once again. And for this one, I'm going to give you the formula. Once again, we are trying to represent this two resistors as a total resistance. What's the effective resistance or total resistance? And the formula is given by 1 over R effective equals to 1 over R1 plus 1 over R2. Yes. And that's it. That's it. So let's just jump right into a question and try to apply our understanding. So over here, let's construct the circuit again. R1 and R2. And in this case, I'm going to tell you that R1 is, let's say, 3 ohms and R2 is 2 ohms. And the question is, what is R effective? So go ahead and pause the video and just think about it. You can write some working. All right. Okay, so first thing to note is a parallel circuit. So we have this equation that 1 over R effective is equal to 1 over R1, which is 3, plus 1 over R2, which is 2. Yep. And so we try to simplify this. You can key into a calculator, or you can use math and solve it. But in any case, this will give you a 2 over 6 plus 3 over 6. And then 1 over R effective. This gives you 5 over 6. And remember, this is 1 over R effective. That's not what you want. You're looking for R effective itself. And so you have to flip the fraction on both sides. So R effective over 1 is simply R effective. And then, there you go, 6 over 5. Of course, in physics, often we do not use fractions, so convert it to decimal, and that gives you 1.2 ohms. There you go. So I can show you a quick derivation, which is applying V equals to IR, because you can see the current going through here, let's call it I1, and the current going here, this I2. Let's say we apply V equals to IR. This is V of the battery, which we also know is the same potential across R1 and R2. Then we can say that for R1, we can say that V equals to I1 R1. And therefore, I1 equals to VE over R1. And then we can say that for resistor R2, that VE equals to I2 R2, right? And therefore I2 equals to VE over R2. And based on these two things, what do we know about I1 and I2? If we look at the top here, I1 plus I2 equals to I total. And so for I total, you can say that for R effective, imagine if it is R effective, that means we represented it all as one resistor. We can say that VE equals to I total multiplied by R effective. And therefore I total equals to VE over R effective. And based on these three, this, and this, we construct the formula that we knew previously, which is that I1 plus I2 equals to I total, and therefore VE over R1 plus VE over R2 equals to VE over R effective. And therefore, you can see all the VEs, we can divide both sides by VE, and that gives us 1 over R1 plus 1 over R2 equals to 1 over R effective. And there you go. That is how you get the formula, this formula. This is for resistance. And there you have it. This is the full picture for parallel circuits.